Hello, welcome to the second unit, matrix eigenvalue problem and quadratic forms. In this lecture, we will see how to determine eigenvalues and eigenvectors of a matrix. Already in one session, we have seen this one. So this is a second module. We will cover some more problems. If you look at this problem, find the eigenvalues and eigenvectors of A equals to 1, 0, minus 1, 1, 2, 1, 2, 2, 3. Also, he is asking determine whether the eigenvectors are orthogonal. Determine whether the eigenvectors are orthogonal. So first we have to calculate the eigenvalues and eigenvectors of this matrix. Next we have to check whether the eigenvectors are orthogonal or not. So the procedure is first we have to get the characteristic equation for the given matrix. So to get the characteristic equation, we have to write the formula is this one. Det A minus lambda I equals to 0. So A is this one minus lambda I is nothing but it's a unit matrix of order 3 by 3. That means 1 0 0 0 1 0 0 0 0. If you multiply that with lambda, you will get lambda 0 0 0 lambda 0 0 0 lambda, and if you subtract that from this matrix, the given matrix, you will get this one, which is 1 minus lambda 0 minus 1 1 2 minus lambda 1 2 2 3 minus lambda. So which is a determinant of third order. So if you expand this one, you will get lambda cube minus 6 lambda square plus 11 lambda minus 6 equals to 0. How to expand this determinant? I hope everybody know. In your intermediate we have done already, right? So it is very easy. So if you expand this, you will get lambda cube minus 6 lambda square plus 11 lambda minus 6 equals to 0. So if you write it as, if you factorize that one, you will get lambda minus 1, lambda minus 2, lambda minus 3 equals to 0. From this, lambda equals to 1, 2, 3. So total we got 3 eigenvalues here corresponding to this matrix A. Now I have to get the corresponding eigenvectors. So for that I have to consider the system, that is A minus lambda I into x equals to 0 vector. What is A minus lambda I? Nothing but this one only, the matrix 1 minus lambda 0 minus 1 1 2 minus lambda 1 2 2 3 minus lambda, and x is nothing but column vector of unknowns, that is x y z 0 0 0. So this is the system. Now first I will calculate the eigenvector corresponding to lambda equals to 1. So substitute lambda equals to 1 in this system, then you will get 1 minus 1 0 0 minus 1 1 2 minus 1 is 1 1 2 2 3 minus 1 is 2. So now I have to reduce this into upper triangular matrix. Before that, if here the first row, if it is 1 is there here, it is comfortable. So that's why what we are doing is we are swapping the rows. So I am sending this second row to first row, and we are bringing that first row to second row. In the next phase, we are sending that second row to third row, and we are bringing the third row to second row. So for that, we are using this operation. R1 and R2 are interchanged, then R2 and R3 are interchanged. Then you will get this matrix 1 1 1 2 2 2 0 0 minus 1. Now we will reduce this to upper triangular matrix form. So for that, what I am doing is here R2 minus 2R1 I am doing. Then if I multiply this entire thing with 2, 2 minus 2 0, 2 minus 2 0, 2 minus 2 0. So this is the matrix we got. From this, what we will get by back substitution, minus z equals to 0, one equation, x plus y plus z equals to 0, the other equation. So minus z equals to 0, from that z is 0, another equation is x plus y plus z equals to 0. So from that, if I plug in z is 0, x plus y is 0, so x is minus y. So what I am doing is I am choosing y is k, then my x is minus k. Therefore, the eigenvector xyz equals to, what is x we got? Minus k, y is k which selected, z is 0. So from this I taken k outside, then I will get minus 1, 1, 0. K is a constant, a scalar which is not equals to 0. So if I choose k equals to 1 for simplicity, I will get minus 1, 1, 0, which is an eigenvector corresponding to lambda equals to 1. Next, for lambda equals to 2. So I will substitute lambda equals to 2 in the same system. I will get this one. Now, what I will do is, I am swapping here minus 1, 0, minus 1, 1, 0, 1, 2, 2, 1. So I am swapping R2 and R3. So if I swap R2 and R3, I am going to get this one, 2, 2, 1, 1, 0, 1. Now, I want to make this as upper triangular matrix. For that, these are the row operations I am performing. So R2 plus I am multiplying this row with 2 and I am adding. Therefore, you will get 0, 2, minus 1. Similarly, R3 plus R1 gives 0, 0, 0. So from this, by back substitution, what you will get is x minus z equals to 0. From this, you will get x is minus z. Next, 2y minus z is 0. From this, y equals to z by 2. So I am choosing z is k. Then my x is minus k and my y is k by 2. So the second eigenvector I got is xyz. Instead of xyz, substitute these values. X is minus, what we got, minus k, and y is k by 2 and z is k. So directly I taken k outside. If I choose k is 1, I will get here. Suppose if I am choosing to avoid this fraction, if I am choosing k is 2 here, I will get minus 2. 2 by 2 is 1 and 2 into 1 is 2. So this is the eigenvector corresponding to lambda equals to 2. Next, eigenvector corresponding to lambda equals to 3. So same procedure we will adopt. We will substitute in the given system. Therefore, you will get this equation. We will reduce this into upper triangular matrix, right? So we'll get this equation. So from this, by back substitution, I will get minus 2y plus z is 0. From this, y is z by 2. Similarly, x minus y plus z equals to 0. From this, x equals to minus z by 2. So I am selecting z is what? K. Then x is minus k by 2, y is k by 2. So the third eigenvector we got is 1, minus 1, 2. So the eigenvectors what we got for the corresponding eigenvalues is, these are the 3. So, and not only he is asking check the eigenvectors are orthogonal or not. For this, what I am doing is I am calculating x1 transpose x2. If I calculate x1 transpose x2, which is nothing but the dot product of these two, I will get minus 1 into minus 2 plus 2 and 1 into 1 plus 1 plus 2 plus 1 plus 3 plus 0 into 2 is 0. So clearly it is 3, which is not equals to 0. Similarly, x2 transpose and x3. If I calculate, I will get minus 7, which is also not equals to 0. But if you calculate x1 transpose x3, it is 0. Therefore, these two eigenvectors are orthogonal. That is, x1 and x3 are orthogonal, whereas x1 and x2 are not orthogonal. Similarly, x2 and x3 are not orthogonal. So this is one type of problem. Next, we'll see one more problem, where in the first problem the eigenvalues are and all are distinct. So in this problem we'll see, find the eigenvalues and eigenvectors of, where here in this problem, if you calculate the eigenvalues, we got the eigenvalues is minus 3, minus 3, 5. That means eigenvalues are repeating here. Okay. So now, first I will calculate the eigenvector corresponding to lambda equals to minus 3. So I will substitute this lambda equals to minus 3 in this system. Same procedure. So I will get, instead of lambda, I have to substitute minus 3. So minus of minus 3 is plus 3. So minus 2 plus 3 is plus 1. 2 minus 3, 2. 1 plus 3, 4. Minus 6, minus 1, minus 2. Lambda is minus 3, so it becomes plus 3. Now what is the procedure? Reduce this into upper triangular matrix form. So then you will get this one. By back substitution, we got x plus 2y minus 3z equals to 0. From this, x is what? Minus 2y plus 3z. So here I have to choose y and z. So what I am doing is I am choosing this z is beta and y is alpha. Then I will get xyz equals to, so I selected what? Y is alpha. So y is alpha, z is beta is selected. If I substitute y is alpha and z equals to beta here, so I will get x equals to minus 2 alpha plus 3 beta. So this first what I am doing is I am taking out alpha. Alpha, if I take it out, I will get minus 2 1 0 plus beta equals to, so I can write this as linear combination of two vectors. Here alpha and beta both are not equals to 0 simultaneously. Simultaneously they are not equals to 0. Simultaneously if they are equals to 0, you will get a 0 eigenvector, which is not possible. And alpha and beta are scalars. So you can choose any values for alpha and beta. So what I am doing is, for simplicity's sake, I am choosing alpha is 1 and beta equals to 0. I will get the first eigenvector. Next I will choose alpha equals to 0 and beta equals to 1. I will get the second eigenvector. So this is the procedure you have to do whenever the eigenvalues are repeated. The third one is a distinct one, lambda equals to 5. It is exactly similar, right? So what you will get is, here the equation is this one, x equals to minus z and y equals to minus 2z. So choose z equals to k and x equals to, if you choose z equals to k, you will get x equals to minus k and y equals to minus 2k. Therefore the third eigenvector is, if you choose k is 1, you will get minus 1 minus 2 1. So this is the third eigenvector. So this is the procedure you have to do whenever the eigenvalues are repeating. So in the first problem, the distinct eigenvalues we have seen. So in the second problem, the eigenvalues are repeating. The eigenvalues are repeating. So procedure wise it is a 100% similar. The only difference comes is whenever the eigenvalues are repeated, right? So you must be careful in choosing alpha and beta. And here one more thing you can observe is algebraic and geometric multiplicity of an eigenvalue. This is very simple. Algebraic multiplicity is nothing but how many times it is repeated. Geometric multiplicity means for that particular eigenvalue, how many eigenvectors you got. For example, let us go to the first problem here. Okay, the first problem is where all the eigenvalues are distinct. We got the first problem, the all eigenvalues, if you see here. So if I am asking what is the algebraic multiplicity for lambda equals to 1, means it is 1 only, because 1 is not repeated. For 2 it is 1, for 3 it is 1. Next, coming to the geometric multiplicity, means for lambda equals to 1, how many eigenvectors you got. So in this case, for each and every eigenvalue, you got the corresponding eigenvector is 1. So in this case, algebraic multiplicity as well as geometric multiplicity both are same. Coming to the second problem, if you see, here the eigenvalues are repeated. That means lambda equals to minus 3 is repeated. Therefore, the algebraic multiplicity for the eigenvalue lambda equals to minus 3 is 2. For lambda equals to 5, 1. Similarly, the eigenvectors for lambda equals to minus 3, we got 2 eigenvectors, and for lambda equals to 5, 1. Therefore, the geometric multiplicity for lambda equals to minus 3 is 2, and the geometric multiplicity for lambda equals to 5 is 1. And the note is here, the geometric multiplicity of an eigenvalue never exceeds its algebraic multiplicity. So the geometric multiplicity of an eigenvalue never exceeds its algebraic multiplicity. So this is the note you have to remember. Okay, I hope you understood this lecture. So I am Srikanth Reddy. Thanks for watching. I will see you in the next